So we got the delta method estimation of the uncertainty, or of the precision of our estimate of long run inflation, which was 2.31, and then sigma, the dispersion of the estimator itself ended up being 0.9. Right, and we're showing this with green band. So that was with delta method. So let's try now using bootstrapping. So when we're using bootstrapping, I'm following Shamway and Stauffer's text, example 336, right? So this is the textbook, it's fourth edition. If you're interested, you can find example 336, and they talk about bootstrapping the parameters, the parameters themselves. But in this case, what I'm going to do is the following. I'm going to bootstrap the distribution of this estimator. So we are calculating this estimator, right, of the long run mean as a function of the constant and phi, autoregressive coefficient of this ARMA process, right? So we get constant and phi, and based on these we calculate the long run mean of y. Now with delta method, what we did is we tried to apply some approximation using variance covariance matrix of these two coefficients of the regression. We try to get the variance or dispersion of this estimator, right, of this estimator. We approximate it with delta method. Now in bootstrapping, what we're going to do is this. We will regenerate this series. So we will look at the errors of the series innovation, and then we will bootstrap. We will randomly sample the errors, and for those errors we will create new realization of the process, and then we'll re-estimate the model on it to obtain C and phi. We'll do it many times. So this is what I'm doing in bootstrapping, right? This is a parallel version of the bootstrapping. So well, first of all, my fit residuals, right, fit regression has many outputs, and one of them is residuals. So what I'm doing here is, in this function get long run mean for one simulation, is the following. I will sample using a random number generator. I will sample from the residuals with replacement. I will sample 40, like the same length of the series, but random sample of the residuals. I'll get these, and then I will go and create a new series. So using my starting point y0, like it's January 1st 2012 PC inflation, right? So using this inflation point, very first point only, I will recreate a new like a new sample of the time series. So I'm using the residuals, but I'm randomly sampling from residuals. I'm shuffling them, and then with replacement, and then I'll go and create a new series. And then I will fit this series into the same model. But when I'm creating this series, I'm using the parameter estimates, right, from my original model. So I'm using parameter estimates original model, but I'm resampling residuals. I create new series here, simulation, and then I fit into the simulation and again obtain the results of the simulation. And from these results, I will calculate this mu, my long run mean. That's how I will repeat this process, let's say 1,000 times, and once I'm done with that, I will get the distribution of this estimator. So I bootstrapped the distribution of this. Okay, where am I? Of this estimator, right? So I created 1,000 simulation of this estimate, because we said estimator is a random value. It's a random function of the data set, and then I simulated new data set, and then estimated constant and phi on this new data set, and calculated my new long run mean estimator. So that is what my process is doing here. I will not run it because it's pretty slow. 1,000 is, and then refitting is pretty slow. But what I will do This I'm done. I'm doing some parallel processing here. That's not very important. What I did is this, like from bootstrapping, I got my long run mean, right? It's easy because once I got my results, I can just get the mean or the median. So my mean is 2.38 and my median is 2.37, pretty close to each other. And then the dispersion of the long run mean, which I just calculated, is 0.72, which is quite, it's lower than 0.89. Remember, the delta estimate was 0.89, which is an approximation. And bootstrapping is probably a better approach in this case. Bootstrapping is giving me a smaller number. Although it's a smaller magnitude, it's still quite a lot of dispersion. So my conclusion doesn't change. 2.31 inflation, it's still compared to 0.72 sigma of this estimator is quite close to 2%. So I'm going to stick to my theory that Feds are trying, like the data shows that Feds are trying to hit that 2%, right? Now, what is interesting is, like I said, the distribution, right? So these results which I got from the bootstrapping, I have 1,000 realizations of this mean, of this long run mean. So I can look at the kurtosis and skewness of this distribution, and you see they're very close to normal. The skewness is 0 and excess kurtosis is 0.07, basically also 0. So, and that's why I'm saying the distribution of my estimator seems to be very close to normal, right? So that was a comparison of my delta estimator. So it is an approximation. It was overstating my dispersion, it seems, but it's not too bad, I think, for an approximate in this case.